Welcome to Fun with Science, Engineering, and Technology. I'm Mr. Ross, and today we're going to discuss robots, right? And we have some special guests with us. First of all, Melissa, which you all know, but school's out, and Melissa actually volunteered to come back in here, even though school is not in session, and help us out with our television program. Our real expert on the robot and the programming of it is Mr. Bill Cridland, all right? Who's with us today. And Bill, a little bit about what your background is.
Yes, as Jim has pointed out, I'm Bill Cridland. I teach computer programming, specifically C++ at Nashoba Regional High School at Bolton, which is just south of us. I teach 1 day a week. Also, we are interested in robot engineering, and the reason for our interest in robots is that we find that students seem to or tend to go to sleep when they're being taught programming, whatever program it is. And so what we've decided to do is to build or construct ourselves a robot with the object of programming it so that the children will be able to see the end effect of the programming. That is, it's going to walk, it's going to avoid obstacle, and the rest. That's the introduction. I think I'll stop at that point because there's some other features that we'd like to discuss, if that's okay.
All right, that's fine, Bill. So basically we have a little robot, but you teach C++, right?
Right.
So where did you learn C++? What did you do before that?
I was an engineer for Raytheon at Marlborough, and I was actually a memory design engineer at Marlborough. And people used to come in with software programs to put in the memories that I was designing. But I was so interested in the programming, I thought, well, I'll see if I can do it myself. So I started to look into different facets of programming, starting with C, the C program, and then I gravitated to C++, and I became quite good, and I changed over from hardware to software. And as a consequence, when I retired, I started teaching C++ at Nashoba Regional High School, and I've been doing that for the last 6 years. And we've had many successes, many failures, of course. But our interest now is to motivate the children, and to do that, we are interested in programming robots, because robots will give you or define the end effect. What does it do? Now, robots themselves it's just not just walking around, although that's one of the facets. The other thing is its behavior. And we're interested in mimicking a bug, in this instance, of what it does when it reaches an obstacle. When it reaches an obstacle, it'll do two things. It'll back away, that is, it'll reverse itself, and then it'll turn either to the left or to the right to avoid the obstacle.
So we could have sent this to Mars this last summer with the Spirit rover that we have up there on Mars right now, right? Because it has some intelligence of its own, right? It's not going to get itself hurt necessarily. And in the case of the Mars rovers up there, it takes like 10 minutes to get the signal to them and 10 minutes to get it back. So they're sort of remote controlled, but there's a whole time span there where we don't know exactly what's happening. So if this thing happens to be moving up there on Mars, it could fall in a crater or run into a rock or whatever. So it has to have a little bit of intelligence on it, right? To say, whoa, hold it. I don't want to run in. I don't want to drop in that hole.
Yes.
And basically, that's what you have here.
Yeah, absolutely right, Jim. And that is a good analogy, by the way. The moon rover takes radio frequency signals from NASA. It's beamed up to the rover, and then the electronics is very similar to what we have here, but in a much more advanced state, because they've got more money than I've got. But they do the same things. They command it to let it go left, right, and also it also has sensors in the front. I think they also have radar type sensors other than the other sensitivity process called infrared. So these are radar signals that we're sending out in this particular model, and I think the rover also uses the same technology.
Right. So can you explain a little bit about the different parts on our
Yes, the parts of this, of course, is that it's battery operated at the moment. It also, we are going to build a little gadget which we can then control it from an external box to make it walk, make it even actually talk. This particular model here has got sound, it's got radar sensors. It sends out a signal, and when it sees an obstruction, it receives the echo, it's interpreted by the electronics here, and then we can equate the distance from the sensors to the object in front of it. Now if you look at this chart here on the wall, on the board here, it's got distance, speed and time. Now if I'm going very simple, if you've got a car that's going 50 miles an hour, in half an hour the distance covered is 25 miles. We all understand that. Now this one here hits that and comes back again, so we have to divide that by 2 because to get the distance, because it has to go there and back again, which is the time duration, and we have to divide it by 2, and then we can equate the distance. When it detects that obstruction there, the electronics there says reverse, and it reverses when it sees that, and then the next command, then it'll turn either left or right. Do you understand? And inside its electronics it has a scenery of everything in front of it. That is, it knows exactly where all the chairs are and all the rest of it. For instance, if we were to move the chair, it would then recompute here. It would look around there and note that something is different. The chip itself is this guy here. It's 18 pins. It's a small little IC, and it has all the behavior programming, the walking intelligence, and the radar situation inside that little chip there. It's 18 pins. It's an integrated circuit chip, and this one is plugged into this little board here. We also have 3 motors, 2 motors here and 1 motor in the left to operate the legs. Now this bug particularly has 6 legs, so we have to examine a 6-legged bug to examine its walking behavior. And there's a special code which we use to make sure that only 3 legs at a time are on the ground. The other 3 legs are up in the air. Now the reason for that is that we want it to walk either this way or that way or that way, and we need 3 legs, 3 always on the ground. There's either 2 and 1 there or 2 and 1 there, and the reason for that is we need the bug to be stable. If we had a 4-legged thing, it would be it would be actually flopping around.
So that's an old technology. That's like
that's
the old milking stool. Every farm boy knows that a 3-legged milking stool is more stable than a 4-legged.
So we said, okay, let's follow the bug, and it's been around for thousands of years. So we did that approach. Any questions now at that point, Jim?
No. What controls the intelligence in it that makes it, you know,
good.
No.
What we do, we use a very good question that. We use a programming language called PIC, that's Portugal, India, Canada, PIC BASIC we call it. It's one of the derivatives of BASIC, which are several versions of it. This one is called PIC BASIC. And the reason for that is that we actually are interested in the actual program for that particular chip. It's called PIC BASIC. That program has got code in there, and we have routines built in, and this is the routine here. There's about 3 or 4 pages of it, of code. We have loops, we have different types of variables in here, and all this is to generate the behavior pattern inside this chip to make it do what we want it to do. Now in this particular program, we've done the following. It turns around in 18-degree arcs around for 90 degrees, and as it's going round, it's surveying what's in front of him, and then whatever objects it sees, it puts into its memory. Now then it looks and says, which way can I go? And it's thinking this way, and wherever it sees a gap, it'll go for that gap. Do you understand? That is any questions so far?
Okay, so you have a question, Melissa?
No.
No, you understand everything, right? Okay, so I'm looking at this computer program there, and it's sort of looks like a lot of gibberish. It's some of it sort of English, but then it's not really English. So that's a different kind of a language. That's like another language, right?
Yes. Actually, what we call the syntax is a little bit different from C++. It's called syntax. So, however, you get used to it. It's like everything else, you know. It looks like gibberish, and I look at it, and some days it is gibberish.
When you have one of those
especially when I get it wrong.
Well, you have one of those senior moments.
Yeah. And I can assure you that most people that program never get the program right first time. They always screw up. So this is a standard PIC basic, and this program, but what we're interested in here is to show the children exactly what program is all about and how powerful it is to go into that little chip here. And there's thousands of lines here that we can use and stick into this chip. And we do this automatically with electronics.
So now then, that little chip understands this
Yes,
language.
it does. Yes.
Well, I always heard that the computers are ones and zero things. It's either on or it's off, kind of a switch operation.
Yes.
And how does it get? So how does it really understand this?
Well, first of all, the PIC basic is geared for this particular chip.
Okay.
And the reason for that is that because it says, I don't want to go too technical, but it's called IOs, input, output. I've got our IOs, which we then stick on what we call variables. And there's a lot of them. There's triggers, there's echoes, there's pulses that go out, pulses that come back in. They're all geared for this particular chip. What we do here is to write a program, and we use loops, if-then decision-making code, which then will generate the behavior of that little bug at that moment. Now we have other ways of doing it, but at the moment we've done that one so far. Now the next move after this is to change from this PIC basic, and we're going to go over, we're going to try it at C language first, which is the older C, and then from the C then we're going to gravitate and go up to C++, which I teach at Neshoba Regional High School.
And C has a different syntax than this.
Yes, that's very astute, Jim. The syntax is quite different. However, the actual loops and the decision-making, if-thens we call it, are all the same actually, except the syntax is different. They don't have semicolons at the end of the paragraphs, for instance, in this code, whereas it's important to have it in C++. So unless you have gone through C++, it's a little bit different, but it can be changed over. Any questions, Melissa?
No.
So, Melissa, you understand all that, right? Where's
Yeah.
the on-off switch, Melissa? How do we turn?
We have a little toggle switch here, which says power, and I'll just put it, it might jump off the thing, so. Notice it's turning around, it's surveying everything in front of it. Going forward and so forth, and it'll drop off the page. Did you notice that? It's going round and it's surveying everything. It was looking at you actually,
Yeah.
and getting the things. Now, to demonstrate this proper, we'll put it on the floor where we have a lot of space. But before we do that, any other questions, Jim?
Yeah, so basically this the thing that makes it smart is the software, the program,
Yes,
the
the
programming.
software, yes, yes.
So, and software is a very important thing nowadays. Besides all the engineering that went in, this is a very complicated machine. I mean, you look at it and it's a little six-legged bug, but it's got a radar on it. It's got a lot of mechanical stuff in it, and motors and electricity and all that sort of.
These are servo motors,
Right.
I call it. Yeah.
And but the thing that makes it all hang together and work is the programming. What
Yeah.
this
It's that
programming
chip
that you
there.
wrote here, all right?
Into
And
that.
then you take that and you store it in the chip. So everything we have nowadays just about has programming in it.
Yes, well,
It has some sort of software. My cell phone, right? It does all kinds of magic things. And the reason it does all kinds of magic things is because of the software, right?
yes.
And
Let me just also, probably the people who are watching the program have seen the advert on TV. Actually, it's putting on every other day. They've got this little plastic-looking, it looks like a disc, and it's actually a programmable carpet sweeper. And what happens, have you seen it, Melissa? And this thing goes around, and when it touches an obstruction, it backs off and goes around. See, but their detection is touch. Whenever it touches, you've got a little contact switch inside of it, and it's not so advanced as this. This is a radar, right? And it doesn't go anywhere near the obstructions, you see. So this is a little bit more advanced. But the little thing that you can get for, what's it, $129 or something? Looks, my wife wants one, actually. I mean, she's fed up doing the floors, so yeah, it works.
right. So yeah, the software, the programming is a very important thing in our,
Yes, yes,
life now, and it is a super kind of a job for some young individual that wants to get involved in engineering and make a considerable amount of money, is to go into the programming side of it. And it's a lot of fun. We got a lot of youngsters out there right now are playing all those video games, and the reason those video games work is because of the software behind it, right?
Yeah,
that makes it all work. And they don't realize that writing the software for the video game is a lot more challenging, right, and probably a lot more fun than actually sitting there day in and day out playing that game, whatever it may happen to be. So it's a very good thing for people to get involved in, and it doesn't take a whole lot either, right? If you had a PC at home, you can write computer programs.
Yeah.
Right? Because basically all you need is, what do you need? You need.
Well, we have small little electronics to program this, which we do via our computer. We just plug it into the printer port, and it prints this automatically. That is, the code goes into this automatically via our computer. We have the programs on our computer, of course. And we have to compile the computer after we've done it. As I said before, sometimes it doesn't work, so we have to debug it like everything else. I'd like to mention too, probably before we dismantle here, the reason for this is we're interested in the children learning to program and looking at the end effect. And this will stimulate them. They probably want just to climb a mountain or something, so they're going to put a different program in.
Right.
Yeah, or maybe into they have another scenario, and they'll do the code for that particular situation. This one, you can hear a little beep noise on this, and this also can be made to play tunes or actually speak to you. So we can actually program it. It also has the ability for speech recognition. That is, you can command the bug walk, and the bug will start walking. That kind of thing. So we haven't got it in at the moment. We have the code for that, though.
That's really the advance, because when I first got involved a little bit with the computers, speech recognition was really out there somewhere in outer space, and nobody hadn't developed it yet, and it was sort of a curiosity kind of thing. But now, I go to my doctor's office, and he sits there and he talks to me, and he talks to the computer, right, and he puts all the data into his computer about me just by talking to it. Right? He doesn't hit the keyboard or doesn't do any typing.
Yes.
And In fact, I just have a new car that you talk to, right? You can tell it to switch the radio, change the channels, and all that sort of thing. So the speech recognition is really a great advantage, and it's all software.
Mm-hmm.
All right, as you can see, we've rearranged the set a little bit, and we have our robot bug down on the floor, and what we're going to try to do is to demonstrate its detection capabilities and how it's going to avoid everything. We have all these little objects around, and Bill, what it should do, correct me if I'm wrong, is it's going to go around and it's going to scan the area and record where everything is, and then either back off or take off in a direction where it's got a free path. And why else comes it's not doing anything?
Well, no, first of all, I'm going to switch it on.
Oh, you got to turn it on?
It's like,
I thought you said you were going to program it so that you could say start, and it would start, all right? And you didn't do that during a break while we did that. Okay, all right.
So we're going to, just like a car, we're going to start it.
Okay.
And the only problem I see is probably going to go over that. It sees a cliff there, you see.
Right.
But yeah,
Is
we'll
it
try it.
going
Anyway.
to see the cliff? Probably
Well, it's
not,
going to
right?
go over the top, probably. I don't know. It's now detecting anything in front of it. This is the front. It detected that and it backed off.
I thought for a minute it fell in love with our bear. Now, how badly do I confuse it if when it's not looking at me, I move?
Oh, I wouldn't know that. It just loves that bear.
Mm-hmm. Yeah, I think it's. Okay, there, it's backing up a little bit, and it's still looking for.
Notice that?
Still looking for a place to escape to,
Mm-hmm.
right? Now, how does it know when it's got enough information? Or does it just look for an opening?
It's just looking for an opening.
And it's not finding one. Now, if you were to turn it off right now, so it would reset?
Yes.
Right? And it would, all that data that it's storing about
Yes,
these
it would
things,
go. Yeah.
it goes away. Right? The program stays in there, but
Yes,
the data is
that's
storing.
right. Yeah.
So why don't we shut it off,
Yeah.
reset it, and why don't we put it out there a little bit further to where it can find, maybe find an opening. We had it too well confined in here. It's. All right, so. Oh, it thinks it's got a way out now.
Detected something there.
Mm. So how much memory is in there now?
Repeat that.
How much memory is in it?
It's about 2,000.
2,000 bytes? So there's not really a lot of storage space in it.
No. I'm very pleased it's not going that way.
You don't want it to run off. Right? So it's still searching.
Yeah. Anyway, I'd like to switch it off.
Yeah, go ahead.
Okay. Okay, as we demonstrated that it's actually when it sees that, what we do actually in actual practice, we have a maze. We build a maze. I haven't done it yet, and we actually program the code to get out of the maze. Everybody knows what a maze is, don't you?
Yeah.
And we put it in there, and the thing comes out exactly. It comes out of the maze. That is with a different program. Now, on this particular program, what we've done in the past is to put little bottles or whatever in a circle to make it go a little bit better, because these are kind of undefined objects, you see. I don't think there's anything else except that's how it works, you know. And it's a radar type of detection, not infrared.
So it's actually sending up radio
Yes,
waves and
yes.
bouncing off of things, just like the Doppler radars that
Yes,
the weather people have.
and as I said before, Jim, we are going to include electronics to control it from remote. You understand?
Mm-hmm.
So that we will be able to go in the next room and control it. Now this is the similar things that they use in the U.S. Army for mine detecting and all the rest of it. So we know exactly what's out there.
Yeah.
And we'd rather see this blow up than some of these.
Right. The Army just did a runoff and it had a bunch of people. And I think there were some high school kids out in California who had built what the objective was to build a vehicle which could navigate across the desert by itself, right? And it obviously had little radar. There were several vehicles.
Yes.
And they obviously had little radars and this sort of detectors in them. And one group to build one was a high school group. Right?
Yeah,
It obviously had a little robotic experience and so forth. And I know that Carnegie University just not too long ago built a groundhog, right? And the object of the groundhog was, a few years back we had a big mine disaster down in Pennsylvania, right? And they had a problem getting down in to find the people and so forth. Well, this groundhog, what they did is an old abandoned mine, they sent it down in there, right? And it was very similar to this. I had all the detectors and all the programming and so forth to see if it could find its way around in the mine, right? Same technology as we have here. And it did the right thing. They were very happy because they said they didn't know whether they were going to lose it down in this old abandoned mine or not. They went down in the mine and they come up against something that they couldn't get around, and it said, whoop. And it had remembered the path it had taken to get down in the mine, right, with all the fancy software they had in it. And it just turned around and came back out. Said, I can't go any further. And it was smart enough, smarter than a lot of humans in some cases, and it turned around and came back. So,
yeah, I think your point is well taken, Jim. This is only as good as the program that you put into it,
right.
The behavior pattern.
And the fun part about it is the programming.
Yes.
Just writing the
That's right.
instructions.
And this is what we're interested in, of generating interest in programming.
Right.
But the mechanics is drilling, bolts, nuts. Yeah.
Right. Bolts, nuts, and
Yeah.
6 legs, all right, which are old technology.
Anything you want to add, Melissa?
No?
Okay.
Well, I'm just about ready on this. So we thank you very much for allowing us to demonstrate the robot, and I'll pass it back to Jim. And he can
It's an opportunity we wouldn't have had if you hadn't come all the way up to 495, and I'm sure that you know, some of the youngsters out there will be very interested in building one of these things,
Yeah.
and also going into programming, because that's the real challenge behind those video games that they're playing now is to do the software to make the game play.
Well,
right?
it's just happens that way that our organization, which is called RSVA, has funded us for 2. Now we have a separate kit so that any school can borrow the kit and build it themselves if they wish.
What is RSVA? What is it?
Retiree School Volunteer Association.
Okay, Retiree School Volunteer Association. All right, very good. So that's a group that you belong to?
Yes,
Okay.
and that's what you belong to.
Oh, okay.
You happen to be the treasurer,
Yeah, I have.
which I happily received the money from you for 2 of these kits. One I built, and one is spared in a box which can be given to any of the schools to build themselves, or if not, we'll put it into Neshoba in the fall and they can build it. Because also someone has to do the work of drilling holes and all the rest of it. And that is a part of engineering.
Yeah. Very good. All right, so that's it for today, and we thank you very much for watching, and we'll be back with you next week.
Okay.
Here are some summer safety tips. This summer, children ages 14 and under will be rushed to emergency rooms nearly 3 million times for serious injuries.
There are 85 million bicycle riders in the U.S. About 800 bicyclists die in the U.S. every year.
In 2002, nearly 288,900 children were treated in hospital emergency rooms for bicycle-related injuries.
About 67,000 have head injuries.
If you wear a helmet, you can reduce the risk of head injury by as much as 85%.
If your bike is new, check it out before you ride it. Always check the brakes before riding your bike. Check for traffic. Always be aware of the traffic around you. Learn the rules of the road. Obey the traffic laws.
Always remember to use your helmet.
Everyone needs to use safety equipment.
Helmets are cheap. Wear one.
Protect your head. Wear a helmet.
Helmets save lives.
Have a safe summer.